Today we're going to get into some of the algebra with matrices. And one of the things with matrices is something called a determinant. We've already been introduced to the identity matrix. That's where you have a diagonal of ones along the main diagonal and everything else is 0. And what's nice about the identity matrix is that if you multiply anything by it, you get what you started with. So A times I, AI, is A, is equal to IA. Okay? Now the determinant of an identity matrix is always 1. How do you find the determinant of a matrix? You have this formula. Now the formula I find a little bit hard to remember. It is much easier if you just use diagonals. The determinant formula will always be this diagonal, that's A times B, minus this diagonal. And since that one you're going backwards, that's how you remember that you're going to have to subtract. So your one diagonal minus the other diagonal. And you can either see that a question is asking for a determinant notation-wise by either putting det in front, short for determinant, or absolute value bars around your matrix. Normally a matrix is with square brackets, so when there's straight lines, it's asking for a determinant. So again, I wouldn't remember the formulas. I would just say this diagonal is 8, this diagonal is -9, and so my determinant would equal, notation-wise, what should I write? I'm going to just call this A, and I'm going to say determinant of A is equal to 8 minus the -9, which would be 17. So we always subtract the arrow going backwards. So again, second one, this is 36. Going backwards, this is 36. If I call this matrix B, then the determinant of B is 36 minus 36, which has a determinant of 0, which is going to be important because we are going to find out about inverses of determinants. Inverses of matrices. And we just discovered that matrix B does not have an inverse. Well, you didn't discover that. But I'm going to let you know that if your determinant is 0, you're not going to have an inverse. You can only find the determinants of square matrices. So we have a lot of restrictions on matrices. And matrices that have a determinant of 0 are called singular matrices, and as I already mentioned, they will not have an inverse. And now we have a 3 by 3 matrix, which has the awful formula here, and I'll show you a shortcut to remember it. So the awful formula says, if you took A, you multiply by A by the matrix of what's left if you got rid of that rest of that row in that column. Okay? Then you subtract B. So if I take B, get rid of the rest of that row in that column, and then take the matrix, the determinant of what's left, plus C. So if I went to C, and got rid of the rest of that row in that column, and did determinant of what is left. And we'll probably never use that formula again. Because this is the same thing, but way easier. You rewrite column 1 and column 2 again. and go this way and add them up. And then you do your diagonals backwards and add them up. And you take your blue one and subtract your red one and get the same answer, which is a very nice shortcut for figuring it out, rather than doing the little matrix all the way through. So what does this look like with an actual question? I would rewrite column 1 and column 2. And this diagonal will be 8 plus 0. Wow, that's ugly plus 0, and then this diagonal 4 times 1 plus 4. Then backwards, this will be 16 plus 0 plus -2. So if I call this matrix A, then my determinant of A will equal, from the blue, is 12 minus, and from the red, if I add that together, I get 14. So my determinant of A will be -2. And because the determinant is not equal to 0, this one is going to have an inverse. Now, had you used the formula would have said determinant of A is equal to 2 times this determinant. And this determinant would have been 4 minus 0. I did those diagonals. Then minus, I take the second number, which is a -1, and then do the determinant of what was left, which would be 2 minus 0. And then plus a 4, and the determinant of what's left would have been 1 minus 4. So you would get 8 plus 2 is 10, minus 12 is -2 as well. Whew. I was getting all nervous. If my shortcut gave me a different number, then we'd be in trouble. So here's one for you to try on your own. I'll put up the answer in a second. Don't worry, I have it all on video so you can catch up with what you missed. Okay? If you want to check if your determinant is right, you can do so with your calculator. So what we're going to do is we're going to type in this matrix of 303, -215, 4, -20 into our calculator. So I go second matrix, go over to edit. I make this a 3 by 3, and then I have 3, 0, 3, -2, 1, 5, 4, -2, and 0. So I've got matrix A in there, and then if I go back out of here, and I go back to matrix, between the names and the edit, there was math that you could do. Right? You could do, in one, the determinant. We could figure out the transpose. You could figure out dimensions. You can fill. There's a whole bunch that you can make a random matrix. That'd be fun. So what we're going to do is we're going to find that determinant of second matrix A to see if it's equal to 30 on our calculator as well. And it is. Now, where are we leading with this? And I've kind of given a little hint away in the top right-hand corner, is that matrix that we just did could represent the coefficients of some system of 3 equations and 3 unknowns. Like, let's say you had 3x plus 0y plus 3z equals 5. How do we solve this right now? We would do our systems of equations, eliminate one variable, then get 2 new systems of equations, and then work from there to solve. We're going to see how matrices, and especially how computer programs like our calculator, can make this really easy for us. So we don't have to do it all by hand if we had a calculator. And if we don't have a calculator, we're going to see how we could do it by hand with matrices. Right? There's the T button you can do. If we wanted to find the transpose of a matrix, we could have done that. Second matrix. Math, number 2. That would take our answer as a transpose. Maybe I should have typed in, oops, alpha, second matrix, matrix A first, then did the transpose. It just took them and rewrote them for us nicely in columns. Which, if you needed to use that for some math, I can now store that as B. Okay, because there's some places where you need part of the formula uses transposes. We don't go too much into those formulas. I can show you a couple of them later on, but it is helpful to get the computer to, or the calculator to do that, and then we can store our answers. And this one is really, really nice. Okay, so let's just, I had this equation. I'm going to go back to matrix, and I'm going to edit this matrix A just to show you, because it's so cool. And I'm going to change this to now being a 3 by 4. And you know how I had written this 5, 2, and 7 in green here as a possible system of equations? So I'm going to put 5 in there, a 2 in there, and a 7 in there. And I'm going to go to the math. And choose the ref one of matrix A. And I'm going to change it to fractions. If you solve this, you would find out that 1x has to be 17/30ths. 1y is negative 71/30ths. And 1z is 11/10ths. And those are not very nice whole numbers. So if you were doing a system of equations and solving, you would be really frustrated once you're like, oh my goodness, look at the fractions that are in my answers. And I have to solve that. So now we're seeing how matrices, and we'll see this later, can solve systems of equations. But first, to solve systems of equations, we're going to look at inverses. The inverse of a matrix is the idea that if you multiplied a matrix by its inverse, you would get the identity matrix. It's sort of the thing that undoes it to get the 1 in matrices, right? I mean, an inverse of 5 would be 1/5. When you multiply them, you get 1. Inverse of 7 would be 1/7. We're looking at what we would have to multiply by to get 1. Okay, here's the formula. The inverse of a matrix is 1 over the determinant. So the green circled part is your determinant, and this is why a determinant can't equal 0, because you're not allowed to divide by 0. So if your determinant is 0, there's no inverse. Then switch the main diagonal, the order, to D and A. Ooh, that sounded like biology. And then the other diagonal, you just make negative. So if A is A, B, C, D, then A inverse is 1 over its determinant, switch A and D, make the other diagonal negative. And if you do this, you will always get a new matrix that, if multiplied by the old matrix, gives you a perfect identity matrix with zeros in the one in the corners and 1 along the main diagonal. Oh, let's go back to my notes that have nothing written so we can just do them. So I'm going to call this matrix A. The first thing I'm going to find out is my determinant by doing this diagonal, which is 6, subtract this diagonal, which is 5. My determinant is 1. That means that A inverse will equal 1 over my determinant, 1. Technically, you wouldn't have to write that because that's just equal to 1. Square bracket, switch the 3 and the 2, and make the other diagonals negative. A quick check, right? If you took A and multiplied it by A inverse, this is a 2 by 2, multiplied by another 2 by 2. So since the middle numbers are the same, you're allowed to multiply. And since the middle numbers are the same, you will get a new matrix that is, the outside numbers, it's going to be a 2 by 2. I'm just going to rewrite A under here and A inverse, and just remind ourselves, how did we multiply inverses, or how do we multiply matrices together? So A was 2, 3, 1, 5. 2, 3, 1, 5. And A inverse, we just figured out, was 3, negative 1, negative 5, and 2. And I don't need to write the 1 out in front. So if I want to find the following answers, and I'm going to color code them. If I want to find this one in purple, which is going to be in row 1, column 1, I would take row 1, I would take column 1. Right? I take row 1, I turn it on its side, I crash it into column 1, and I'm going to get 6 plus 2 times 3 is 6, and 3 times 5. Something, did I write something down wrong? 2, 1. Oh, man, I wrote my A down wrong. How did I mess my A up so bad? Okay. 2, oh, yeah, gotta go back to the. Okay. 2, 1, 5, 3. 2, 1, 5, 3. There we go. I was like, and here in my first example, the inverse is not working whatsoever. I must have wrote something down wrong. Okay, I'm going to take that 2, 1. I turn it on its side. I crash it into this one. The 2 hits the 3, makes a 6. 1 hits a negative 5, makes a negative 5. Add up the pieces. 6 plus negative 5 is positive 1. Next one. I did this one next in orange. That is still row 1, but it is now in column 2. Row 1 turned on its side, crashes into column 2. I'd get negative 2 and plus 2. That would be 0. Next one, in blue. That's in row 2, column 1. So I take row 2 and multiply it by column 1. Turn it on its side, crash it in. You see you'll have 15 and minus 15, which will be 0. And finally, light blue. Row 2, column 2, take it, turn it on its side, crash it, 5 times the negative 1, negative 5, 3 times 2 is 6, add up pieces, and we get 1. So when you multiply by an inverse, you get the identity matrix. And anything multiplied by the identity matrix is 1. So the second one, I'm going to call this matrix B. I'm going to find the determinant of matrix B to be 3 minus 0. It's just equal to 3. That means that B inverse will be 1 over your determinant, switch your main diagonal, and add negatives on the other diagonal. So B inverse will be 1/3. If I was multiplying B times B inverse to check, I would probably take this 1/3 and just pull it out in the front and deal with it last. Because then you don't have to worry about doing any kind of adding, subtracting with fractions. So if you have a number out in front, that number out in front of your matrix could come out right in front. So if I was multiplying this, I would take that 1/3 out. I would write my 3, 1, 2, and 0. That's my original matrix, 3, -1. Oh, it's -3 and -1. Having a tough time rewriting things. And I would multiply that by my inverse without the 1/3. And if I did that, I have this 1/3 out. When you multiply these together, you're going to find you're going to get this. 3003. And then if you multiply by the 1/3 now, those 3's would become 1's, and you would get your identity matrix. But for ease of mental math, it makes sense to have that 1/3 out in front and do that at the end. So here's the reason. Because we need to divide by the determinant to find an inverse, that's why you can't find an inverse if the determinant is 0. I feel like today we're finally doing some this is different. Matrix multiplication was weird a little bit. Then we did the word problems. Kind of made sense why you might do matrix multiplication. And now we're getting into some inverses. And of course, you can find an inverse on your calculator. So I'm going to go to my calculator. I made a huge, I'm going to go second matrix. I'm going to edit. I'm going to put one of the ones we did into, not that, edit. I'm going to go to B. And I'm going to enter the matrix, which was a 2 by 2, the one that we had for matrix B. Matrix B was -3, 2, 0, -1. -3, 2, 0, -1. So now I can go second matrix B, just 2, and the inverse button is right under the square root button. No, that's the square button. The inverse button is right up in the matrix button. Oh my goodness. Second matrix B. Inverse button is at the matrix button. Just hit the inverse, push enter. And often with matrices, you like to hit the math button and change it back to a fraction. Then you might see that it would be easy to pull out the 1/3 in front. Calculator will always have the 1/3 distributed inside. Well, whatever your fraction is would automatically be distributed inside. So by hitting the fraction button, you could maybe see, hey, I could pull out a 1/3. That would give me -1, -2, 0, and if I pulled a 1/3 out of a -1, I would get -3. Okay? So our calculator can find our inverses as well. 3 by 3 inverses will be calculator only. And I'll show you why in a second. So put this into your calculator. After you hit the fraction button, did you get this? So it's not hard to use with your calculator. The reason we don't teach you the formula to do by hand is because it is a 5-step process in which we'd also have to teach you the adjoint matrix, and you would have to use the transpose matrix. I mean, you can look at the steps. Here's the adjoint matrix, where you find 9 individual little determinants first and figure that out. Nice. That doesn't look like it would take too much time. All right, here's the trick for the determinant. You still have to find your determinant. Once you have your adjoint and your determinant, then your A inverse will be your adjoint matrix divided by your determinant. No problem. We will actually be doing our inverse with row operations later. So we will find out a way to find the inverse of our 3x3 matrix, but not with this formula. You are lucky that all you have to know is how to do it with your calculator. And now we get to see how we use this for solving. And after doing all of this, you probably will still like your old methods for solving 2x2 matrices better. That's okay. It's something new. And maybe you'll like it with a calculator with a 3x3 matrix. So what do? We set up a matrix equation. We set up a matrix equation by making a coefficient matrix A. So matrix A is a 2x2. It just uses the coefficients from the first part. We have a variable matrix B equals to an answer matrix, a variable matrix X, which is equal to an answers matrix B. And we have matrix multiplication here. Dimensions-wise, can you see that this is a 2x2 multiplied by a 2x1? And you would get a 2x1. Look what happens if you take row 1 and multiply it by column 1. You get 4x minus 2y. Take row 2 and multiply by column 1. You get 4x minus 1. Now, personally, if I had this and was asked to solve it, I would probably still use elimination. That would be, I look at this one, that would be my go-to technique. But we're going to see how we can use matrices to solve this. I want to get xy by itself. The only way I could get xy by itself is to get rid of matrix A. But unlike regular algebra, there is no dividing in matrices. So normally if you had AX equal to B, and someone says, can you get x by itself, what would you do? You divide both sides by 8, right? And that would get you x is b divided by 8, and you'd be fine. But in matrices, there's no dividing. There's only inverses. And inverses give you an identity matrix, and anything times an identity matrix is itself. So our goal is as follows. We have matrix A times matrix X equals B. We want to get matrix X by itself. So we multiply matrix A by A inverse. But the interesting thing about matrices is that the order matters. So here's the important thing with matrices. If you multiply it in the front on this side, it's very important that you multiply in the front on that side, because the order matters for matrices. So you can multiply both sides of an equation by something, but where you multiply is going to be important. Now this, A times A inverse, which I'll put in blue brackets here, that is going to end up just being the identity matrix. And the identity matrix times anything doesn't change it. So this is the theoretical idea that we're going to do to solve for this. We're going to say that I've got a matrix equation. If I can multiply by the inverse in front, A inverse times A is equal to 1, the identity matrix. That will get the x by itself. So then my answer for x will just be A inverse times B. Well, what does that look like? First of all, I figured out A inverse over here. Determinant was 4, so we get 1/4. We switch the one diagonal, make the other diagonal negative. And now I just plug this back into the formula and say, well, x would equal this by itself. Yes.
Do we write this at the bottom of the page, or where should we write all
Is it, are you running out of room?
Well, it said like solve the system using matrices at the bottom.
So you could put this is solving it with matrices.
Okay.
So you could fill it in with it at the bottom as well. Or on the side, or wherever you have room. And here, do you see that this is a 2 by 2 matrix multiplied by a 2 by 1 matrix? So we can multiply those together, and you would get a 2 by 1 matrix. How would you multiply them? Well, you take row 1 times column 1, row 2 times column 2, and you'll get -20 and -36. If you put that 1/4 inside, you get that matrix X, which was our variable matrix, is -5 and -9, which means that the X was -5 and the Y was -9. And I have been very unsuccessful in convincing you that this is better than substitution or elimination. Because you would still, and I would totally agree, that you should probably still use substitution and elimination. But this is showing us that matrices allow us to solve for complicated situations. And if you had use of your calculator and you had a 3 by 3 matrix, maybe this would be nicer. Or maybe it would be quicker. Right? So we set it up and we solved it. This is the one we just did, right? Is that exact same numbers? Yeah. So we just did that. So our job, if we're using matrices, is to create our coefficient matrix, our variable matrix, and our answer matrix. Then we would multiply in front on both sides by A inverse. That would get your variable matrix by itself, because A inverse times A is just 1. So what does this look like? Matrix A is just the coefficients, matrix X is XY, matrix B is 5, 0. We have to multiply in front by A inverse to get A inverse and A to go away. We write this out. Determinant would have been 5. Switch the diagonal and make the other diagonal negative. And you get that x had to be 1 and y is negative 1. So I don't know if you noticed in both of these equations that you sort of have your equations set up similar to what you would do with elimination, where your x's are in your first column, your y's are in your second column, your answers are on the other side of the equal sign. So if you got a question like this next one, where things aren't lined up nicely, and we have this extra fraction. So step 1, I would look at that second equation, I'd multiply both sides by 4, and I'd rearrange it so that my x's were in my first column, my y's were in my second column, my numbers were in my third column. Then we can set up our matrix equation, find our inverse, and solve.